Welcome, everybody. In this video series, I'm going to talk about how to understand states of stress and how to understand them from ANSYS FEA results. And this is part of our Introduction to ANSYS FEA video series. So in this, I'll go over a quick kind of, I guess, lecture on some things covering states of stress, and then I will actually show using ANSYS FEA some modeling that I've done on for a 2D plane stress case, and we'll look at those stress results and do some calculations by hand. So I'll go over what is stress just briefly, and then I'll cover the different stresses. I'll go over the 3D stress tensor and the 2D stress tensor, and then again, I'll do an example in ANSYS where I load up a plate and plane stress in two different load directions, and then I'll do them separate. I'll run the analysis separately, so we'll have one load case in a second, and then we'll look at the superposition of those results, and I'll show you how to do that in ANSYS. So what is stress? So stress essentially is force divided by area in a part or element, and it's analogous to pressure in fluids. You can think of it as like an internal pressure in the part or element. And I've shown an example here of a square bar, and we've loaded the bar in the vertical direction. Now, if you wanted to calculate the normal stress on the bar, it would be this force here in the vertical direction divided by the cross-sectional area A. And I've shown that calc. And I'll just cover briefly, if you remember from, say, your solid mechanics course, Hooke's law, F equals kx, where k it represents the stiffness. And this is I guess, another version of Hooke's law, where stress equals the modulus of elasticity times strain. And you can calculate the stiffness for a bar if you plug Hooke's law into F equals kx. You can calculate that for the stiffness for a bar is the modulus of elasticity times the cross-sectional area A divided by the length. And so in this case, in this loading, I've shown here this rectangle that's dashed lines represents the deformed state. So if you pull the bar in the vertical direction, there'll be a contraction of the bar in the lateral direction or the horizontal direction. And this relationship is defined by Poisson's ratio. So the strain in the transverse direction over the opposite of the strain in the transverse direction over the strain in the axial direction is equal to Poisson's ratio. And typically for metallic alloys, that's about 0.3 for many metallic alloys.